So today, I have two programs lined up for you all, and this is, shifting operations. So as you can see here, we are going to use shifting operations. One is, it can be the rotate operation. Okay, ROR. We'll be learning about ROR. Okay, STRH. We are very much familiar with this, but we will look into it again. Then LDRH. ROR, okay, and store. So these are some of the instructions that we'll be looking into, and also we'll be looking into some arithmetic shift operations. Okay, so here we have LSLS. Okay, so this is nothing but your logical shift left. Okay, and yes, actually affects the status flags. And similarly here, this is shift right, the logical shift right operation. And here we have arithmetic shift right, and we have rotating instructions and rotating extended instruction. Okay, so we will be looking into all of these. So before we understand the program, right? So let me just explain the concepts to you all so that we'll be able to understand. Right? So I hope all of you are able to see the screen, right? Yes, able to see the screen?
Yes.
Okay, fine. So as I mentioned, we'll be looking into two types of programs, two types of operations specifically, that is shift and rotate. So how does this happen? Okay. So the first thing that we'll be looking into logical shift operations. So here I have two kinds. One is the logical shift left, and the other one is the logical shift right. Okay, so we'll be looking into these two operations initially. So ARM has two logical shift operations. Okay, so number one, it is LSL, which is logical shift left, and LSR, logical shift right. So you can see that here in these diagrams, right, where we have two types of shifting operations. Okay. Yeah. So LSL is a logical shift left by 0 to 31 places. So when I say 0 to 31, it means I have the option to actually alter, okay, how many bits I need to shift. Okay, so let us take this as an example here. Okay, I am using LSL, #4. So let us assume that this is my data here. Okay, so my data, I have some random data here. Okay, 101001001. Okay, and so on and so forth. So this is my 0th bit. Okay, and 0, 1, 2, 3, 4th bit. Okay, 27th bit and 31st bit. So what I'm trying to do here is I'm trying to shift left by 4. Okay, so you can see that, okay, it is shifting left by 4. So this 1 comes here, okay, and the 0 actually comes here. So all this data that is here is lost. Okay, so you can find that these data, whatever is there is gone. Okay, I do not now have access to this data. Just a moment. So this data I do not have access. It has just shifted left. And what happens to the remaining bits? The remaining bits, okay, in the LSP side is actually going to be filled with zeros. Okay, so you can see here it is filled with zeros. So this is the operation of logical shift left. So I hope you have understood how this works, isn't it? Right. So now let's move on to the next one, which is logical shift right. The same operation, right? So what is going to happen? You will find that this 1 is coming here, okay, and then this 0 is coming here. So you are actually shifting the data, and whatever is the remaining bits, okay, here it has been appended with zeros at the LSB side. And then here at the MSP side, zeros are filled. So this is about your logical operations. So any doubts here? Can I proceed? So the most important thing here is that the vacanted bits are filled with zeros. Okay, so that's the most important thing that we need to concentrate here. Okay, fine. So now moving on to the next one. Yeah, the arithmetic shift operations. So now arithmetic means I have access to positive numbers, negative numbers, but then in logical, I didn't have such options, right? I couldn't think of positive numbers or negative numbers. Now, usually we have seen, positive numbers being represented by 0 in their MSPs, and negative numbers are represented by 1 in their MSPs, right? So we have even looked into few programs with regards to the same. So here, we will be taking that into consideration, okay? And we will be seeing how these are operated. Fine. So let us take it one by one, and we will see how this arithmetic shift left operation happens. Okay. So ARM has two arithmetic shift operations, namely arithmetic shift left and arithmetic shift right. So these are the two most important shifts that you can actually see: shift right, shift left. Okay. Now, arithmetic shift left is an arithmetic shift left from 0 to 31. So again, here you have option of moving the bits from 0 to 31, right? So based on what number that I'm giving, the hash number, right? Okay. So it is also, same here with regards to logical shift. So when I do SL, okay, when I do a shift left, then 4 places are actually shifted. So we will actually look into how this arithmetic shift and logical shift are different. Okay, so the vacant bits at the end of least significant end of the word are filled with 0. So it is as good as your LSA. But then when we actually compute, okay, when we actually check, then the values are going to be different. Okay, so we will see that. And next, suppose I want to do, let's say, a positive value, okay, for a positive value. So I do a shift right, okay, and just a moment. Yeah, so I do a shift right, okay, and then I give a hash for some positive value, okay. So in that case, what is going to happen is it is going to be shifted, okay. You can see that this 0 is actually coming here, and then there are 4 places here, okay, 4 places which are actually filled by 0, okay, and then this 0 comes here. Now suppose I do a negative value, okay, arithmetic shift right with a negative value, then what happens? You can observe that this this bits are actually filled by ones. Initially the data didn't have anything, right? Now I have the option to manipulate what my MSB bit is going to be, but here I didn't have that sort of option, right? It was all with zeros. But then here what is happening, it's going to be filled with ones. So this shows that it's a negative value. It's a negative value. So students, up till this point, any doubt? Can I proceed? Yeah. Okay.
Yes, sir, you can proceed.
Yeah. Thank you, students. So next, next you might ask me, how is this shift and arithmetic operation the same, right? So we will take an example here, okay? And on the same number, we will perform both shift and arithmetic operations, okay? Which means the logical and the arithmetic operations, okay? So of course I have put it here a little extensively, okay? So we will anyway just take this as an example, and I want you to actually work out and put it in your notebooks. Fine. To show the difference between logical and arithmetic shift, right, consider an LSR and ASR. So what we will do here is, in order to see the difference, okay, we will take an LSR operation on the same number and also an ASR number, ASR operation on the same number. Okay. So, let us take this as an example. So the value to be shifted here, we will just take it as 112. Okay, 112. I'm just taking this as an example. Okay, I want you all to take a different example and do a manual calculation for this. Okay. So the value to be shifted is 112. Okay, so let's take the binary value of this. So this is going to be 0 triple 1 0 0 0 0. Can someone confirm and tell me if this value is correct? Is that binary value correct for 112? Is the value right? Let's do a conversion from either binary to decimal or decimal to binary, anything. And just check if these values are proper. Yeah, are we getting this value? Okay, thank you. So we will get 0 triple 1 and 0 0 0 0 for 112, right? So now we will perform a logical shift left. Okay, that is 3 times. Okay, so this transforms the bit to be, okay, so this is actually shifting left, isn't it? Logical shift left. So what is going to happen? We are going to see that these ones are going to be shifted here. Okay, so 3 times. So these 3 zeros are going to get cancelled, right? So these 3 zeros are going to get cancelled because it's a 3 shifted value, right? And these ones are going to come and sit here. So that is the thing that we get here. Okay, that's the value that we get here. Okay. So now if we perform an ASL 3, okay, ASL hash 3 again, so this transforms the bit pattern to the same value, okay, which is 0 0. As you see, that ASL and your arithmetic and logical shift operations are the same, but then we have the option of changing the negations, right? The positive value and negative value. So that is the specialty of arithmetic operation. So suppose I have a minus 112. So I think all of us have learned, the complement technique, right? So how do we take a complement, right? And how this operation is done. So first we take the 2's complement. So how is this 2 complement done? We take the 1 complement of that value, whichever number, and then we add 1. So it becomes a 2's complement. Okay. And finally, we get this value. Okay, this value becomes, I'm flipping the value, that is doing the 1's complement, and then I add 1. So finally, I'm ending up with this value. Okay. Now, if I perform LSR 3 operation, okay, that is shift right, okay, shift right operation on this one. So this shifts the 3 bits to the right and fills the vacated bits with 0. So what is going to happen? These 3 are going to get nullified, okay, because it is a shift right, isn't it? So yeah, so 3 bits are going to go, and the vacated ones are filled with zeros. Fine. So we can see that this value. Okay, I brought down the value here, 1001, and then 4 zeros. So if I shift, then what is going to happen? It is going to be 00001. Okay. So you can see that this 1 is shifted here. Okay, this 1 is shifted here. So I have these zeros which are left out. Okay, which are gone, and this 1 0. Okay, 0 0 1, and then the remaining ones are filled with zeros, right? So if I take an equivalent of this, so this is going to give me, um, you know, positive positive value, okay, plus 1 and 8.0. Fine. Now, instead, now if we perform an ASR3 operation on this value, okay, so this actually shifts the bits 3 places, and I am going to get a different value here. Okay, I'm going to get a different value. So ASR operation is equivalent to performing minus 112 divided by 2 raised to 3. So 2 raised to 3 is nothing but 2 2s are 4, 4 2s are 8. So divided by 8. Okay, so minus 112 divided by 8. So this is, again, an additional information that I am providing you. Okay, so you can actually do this calculation manually, and you can try and verify the values. Fine. Okay. Now we have still few more operations left, which is rotate operation, right? Now, once we look at this diagram, it becomes very clear and evident to us what is rotate. Unlike shift operation, there were few bits of data that were getting lost based on how much of shift that you're doing, based on the logical right shift or logical left shift. Okay, based on this number, actually those number of bits were lost out. But here in rotate, that doesn't happen. Instead, you can see that the values are retained. Okay, but then the position of the bits are going to change. Now let us say I have a rotate operation of 4 bits. Okay, so rotate right. So what is going to happen? It is going to be shifted right 4 places. Okay, so this 0 is going to come and sit here, right? And this 1 is going to come and sit here, and this 1, okay, is extremely going and coming and sitting towards the MSB side. Okay, and this 1 is going to come and sit here. So it is just like this. I shift 1. Okay, suppose ROR 1. So this 1 comes and sits here. Then again I do another ROR. So this 0 comes and sits here. Right. So again I do one more. So this 1 comes and sits here. So since I have ROR comma hash 4, so this 4 bits are going to come and sit here at the MSB side. So unlike shift operations, these rotate operations do not, the bits are not lost, but then it comes and sits towards the MSB or LSB based on what kind of operation that we are doing. Okay. The ARM processor has 2 instructions, okay, to rotate operations, which is rotate right and rotate right with extend. So RRX, X refers to extend. So ROR behaves much like LSR, okay, which is logical shift right. In that, the bits are moved between 0 and 32 places to the right. However, the rightmost bits in LSR operation fall off the register. Okay, when I say fall off, it means we are losing the values in the register. Okay. In ROR operation, these bits are used to fill the vacant slots. So vacant slots are filled here. Okay, that is in the MSB side, not randomly. Okay, not just zeros, but then whatever is the values left out. Okay, so only those values are going to be filled. Okay, so you have these. So you have these values actually filling it. Right, so these values are filled. Okay, in this way the bits rotate. If the degree of rotation is 32 places, then the output is identical to the input as all the bits would have returned back to their original. So if I keep doing the same thing 32 times, then what happens? It will finish its one full circle, right? One full rotation, and all the bits will come back to its original position. Okay, so now let us take this example. Move R0, R0, and I'm doing the rotate right 3 times. So this will rotate the value in R0 3 places and put the result in R0. Okay. Similarly, rotate, okay, R0 by the value of places in R1. So whatever is the value in R1, okay, so many times it will be rotated, performing the operation on R0 register. The final value is, placed in R2, right? So this is how you have to understand your rotate operations, right? So now let's move on to the next one, right? We have one more thing called extend, okay, rotate, right, extend. So we will see what this operation is telling us about. So rotate and right, extend is our operation with a difference. So there's a crucial difference here. What is the difference? You can just see the diagram here. Okay, it is also involving the carry bit. Okay, so what is this carry bit? So which means I have one extra bit here. Okay, along with 32 bits, I have one more. Okay, so it becomes a 33 bit. So carry flag is also taken into consideration. So that's why the name rotate, right, extend. So there's an extended operation here. So yeah, so it rotates the number to the right by one place, but the original bit 31 is filled by the value of the carry flag, and the original bit 0 is moved into the carry flag, right? So very interesting, isn't it? Suppose I have this value here, okay, and the carry bit is 0, and I just do an RRX, okay, so I do a rotate right with extend. So what is going to happen? Shifting, of course, the shifting operation, and this one, okay, will come and sit here. So this is 0 will come and sit here. So the last bit, okay, the LSB bit will go and actually sit in the carry flag. It will update the carry flag. Okay, and this is as good as, considered like an extension. Okay, like an extension. So instead of having just 32, I have one more bit added, and yeah, so this is how the values are updated. Okay, the original bit 31 is filled by the value of the carry flag. Okay, so you have the carry flag here, so this value comes and sits here, right? This allows a 33-bit rotation, very important, right? So we are, kind of having an extra, okay, extra bit space here, 33-bit operation. Now you might be thinking, sir, do we really need these kind of operations? Do we really need extended operation, or just right, rotate right, or shift left, shift right? These operations would be sufficient. Sometimes there can be, scenarios or situations where you will need an extra bit. So in that case, you can make the full advantage of RRX. Okay, so I hope that all of you have understood. Now let us see one instruction here. Okay, R0, R0, RRX. So what is happening here? It is rotating right extended. So which means extended means I'm not just operating with 32 bits, but then I'm operating with another additional bit, which is the 33rd bit, right? And I'm going to put back the result into R0. Okay, so the result is going to be sitting in R0, but then I'm also involving the one in carry flag. Okay, fine. So any doubts here, students? Any doubts with these concepts discussed? Rotate, extended rotate, arithmetic shift, logical shift. Is it all clear? Okay, fine then. So in that case, we will move into the execution part. Okay, and as I mentioned previously, I want you to manually look into this program for the calculation. Okay, I will not be doing a manual calculation here. Okay, as we have learned the concepts in detail, right? Okay, so yeah, first we will do this program. So we are going to have a normal declaration given here. Okay, area, program, code. Okay, export, start. Fine. So I am loading the register R0 with a value here. Okay, so I'm just giving the data and I'm loading it. Now I am doing a rotate right operation. Okay, so rotate right operation. What is going to happen with this rotate, right? Now this is not, 32, it is 16. So which means half of the bits are, are jumbled, right? So it rotates the contents of R naught, and only the half word is exchanged, right? So if I have 32 bits, only half of it is actually exchanged. So which means, the first half comes to the second half and the second half goes to the first half, right? Okay. Now loading R2 with some value, okay, and then I'm storing this value, okay. I have this value, right? So this value is being stored to the contents of R2. So which means this address remains the same. So if I have to look at the result, then I have to actually go into this address and I have to see what are the contents of that. So you will find that, the value of R1 and R2 will actually be the same, because we are just, it's like copy pasting the value, right? Okay. So next, when we load the values, so which means I am now moving R2's value to R3. Okay. So at this point of time, I have R1, R2, and R3 all the same, right? So now I'm going to do a rotate operation, okay, with R3. So again, now, R3, which means half word, is actually shuffled. First half goes to second half goes to first half, right? And then I increment the address of R5. Okay, so whatever is the address of R5, so you can see in the register bank, right, in the left hand side when you get into the execution. Then the storing operation, that is R4, and this is base plus index addressing mode, right? So we have seen this previously. So whatever is the address, pointed by R2 and R5, those both will actually be added, okay, and it will be, the R4 data will actually be shifted, right? So in this way, we can see that, this program is getting executed, right? So we'll just check for errors, find 0 errors, and then we try to build it, get into debug mode. Right, so I'm going to do a stepwise execution, right? So you can see R0, okay, R0 has some value here initially, and now it should be loaded or updated with this value here, right? So it's updated. Next, what I'm doing, I'm trying to do a rotate operation, and with R1 you can see that this first half and the second half should be changed, okay. So you can see that, this first half, this last half, 0 to 4C has actually come here, then F631 has come this side, right? So there's a shift. Next, I'm going to load R2 with this value. So R2 right now is 0, so I'm going to load it with that. Okay, so once it's loaded, and you can see that the value is updated. Now I'm storing whatever was in R1. Okay, this data R1, I'm storing it in R2. Okay, so what I have done here is, okay, you can see the memory window, right? So I am going to that location, and you can see that, this 3, 1 and F6 are actually shifted to the value which is pointed by R1, and the value of R1 is shifted by the address actually pointed by R2. So R2's address right now is 2 and then zeros. So those I have put it here in the memory window, and you can see the value here, right? So similarly, this R2 value I'm going to shift to R3. So you can see the value here, okay, the register value here. So you can see that, this F631, this value was here, right? So this value is actually shifted to R3. Okay, so load, okay, R3 comma R2. So which means whatever was in R2, okay, that will be moved to R3. So the contents are actually moving. Now I'm going to rotate R4, okay. I'm going to rotate R3 actually 16 times 16 bits, and then the result is stored in R4. So this one will be, can someone tell me now what is going to be the result in R4? Now that we have the data of R3, right? We have 4 zeros and then F631. And after this operation with the data in R3, what is the value that now we're going to have in R4? What is going to appear in R4? Okay, good. So we are going to see, this first half being filled. Okay, so and this is being swapped here. Now I am incrementing R5 with 2. So you can see that it is actually 0 here. So it becomes 2 and moving and incrementing the address. Next, I am storing the value of this R4 with R2 plus R5. Okay, R2 plus R5. So, in this way, the data is actually moving from one point to another point, and you can see that, the values are, rotated, it is shifted, okay, and then it is loaded and stored. So, based on this number, now if you put a 32, then actually, it gets back to its original form. You can try that out. Okay, fine. So, now that, we have seen how this, shifting operation has happened, right? So we will move on to the next one, wherein we execute, the rotate operations, right? We will try to look at rotate operations. We'll do a translate, find zero errors, we'll do a build. Okay, fine. So yeah, so now let us look at this operations. So as usual, first we have the initial declarations, and then I'm loading R0 with a value, and then just a simple program here, right? We're doing a left shift, and S is actually going to change or update the status flags. Okay, so status flags can be your N negative, C carry, B overflow, Z 0, right? And again, I'm going to do a left shift, and that I'm going to store in R2. I'm going to do an arithmetic shift right on the same value that is given here. Okay, F and 00001. So this is going to be like F is going to be 1 1 1 1, isn't it? All right. And then 0 1 is going to be 1 1 1. Sorry, 0 0 0 1. Okay, fine. And yeah, then an arithmetic shift right. Okay, and the value I'm going to store in R1. Now I'm going to rotate the value. Same thing, I'm taking only R0 value, right? Only R0 value is taken, and these operations are done. R0 value, once I do a rotate and then store the value in R2, right? Extended right rotate, and that is going to be with R0, and destination is going to be R3, right? So you can actually, look, you can actually put these values like how I had put them in, rectangular boxes. So you can put it bitwise, and you can try and execute them, right? Okay. So let us start executing now. I'm actually giving the value R0. Okay, so you can see that R0 has some default value. Okay, let us even look at this registers here, right? So if you want to look at the registers, you have to click on the plus button here, just towards PSR, right? So that will actually expand and there you can see all this N, Z, C, B, all this, right? So let me do a stepwise operation. So you can see that now 1 is going to be loaded to R0, right? So F0001 is going to R0, and then I'm actually doing a left shift. Okay, so when I do a left shift, you can check what is the value here, right? So this one you should manually do it. Okay, do a left shift and then convert it to the required format and check if this value is proper. Now again we are doing the hash 1, okay, and that value is stored to R2. Okay, so that is a left shift here. Okay, logical shift right, this is logical shift left, so this was a left shift and this was a right shift. Okay, and next is the arithmetic shift, and the R1 value is going to change. See, R1 value. So this is how arithmetic and logical shifts are going to change, right? So as I explained in my previous explanation, right, before we could start off with the execution, these values do change, right? So you will understand this better only when you start writing them, only when you start executing them one by one, right? So that is when you can actually uh, do it, right? Okay, now the next one, yeah, so the next one is R0 comma R3, right? So this operation is going to happen with extended uh, values, right? Rotate, right, extend. So which means the carry flag value is also be taken up, right? So this value is updated in R3, value, right? So one was there, one is taken up, so it is like as good as adding one to it, right? So yeah, now how do we actually check these values, right? So how do I check the value of R0? Okay, how do I check the value of R1? So if you can actually place the cursor here, okay, then you can find that these values will show up, the values of these, right? And now let me go to this value here, right? F8, okay, 000. So you should be able to see some value there, right? So now how do I access this memory window? Now towards your bottom, okay, towards the bottom, you will actually have two values. Okay, one is called the local stack and the other one is memory. So generally it will be like this for you, right? So you have to click on this memory tab, so that's when these values will come up. Now previously you remember we used to have R0 is equal to 2 and then all zeros, right? So just you can put that value here, enter that value and press enter key, right? So it will show you this location here and you can see the values, right? So this is how you actually even access your memory window. So what I want you to do right now is put these values, okay, do a manual calculation bit by bit, and then you will be able to understand in a much better way. Fine. Okay, students, any doubts? Any doubts? Feel free to ask. Have you all understood? Yeah. Okay.